The first heat exchanger analysis method is the log mean temperature difference method. As mentioned earlier, its main purpose is to allow us to select the best heat exchanger for a particular application. But for us to do this, we must know the inlet and outlet temperatures of the hot and cold fluids and their corresponding mass flow rates. In this method, we first start by selecting a specific type of heat exchanger, then computing the required heat transfer surface area needed to achieve the required outlet temperatures of the fluids. Then we repeat this process for other types of heat exchangers, until we find the heat exchanger type that will require the lowest heat transfer surface area. On the other hand, or for single-pass heat exchangers, such as parallel flow and counterflow heat exchangers, we can simply use this formula to compute for the required surface area, A sub S. Take note that you should first compute for the log mean temperature difference before proceeding with the analysis. Finally, take note that the counterflow heat exchangers is usually preferred over parallel flow heat exchangers. The reason behind this is that the log mean temperature difference of counterflow heat exchangers is always greater than the LMTD of parallel flow heat exchangers for the same set of values for the inlet and outlet temperatures. Due to this, the surface area needed to achieve the required outlet temperatures is lower in counterflow heat exchangers compared to parallel flow heat exchangers. On the other hand, for multipass and cross-flow heat exchangers, we use this formula to compute for the required heat transfer surface area A sub S. Take note that we base the value of A sub S for these types of heat exchangers on the log mean temperature difference of an equivalent counterflow heat exchanger. Finally, capital letter F in this formula corresponds to the correction factor, and its value depends on the type of heat exchanger chosen and on two temperature ratios P and R. For one shell pass multi-tube passes heat exchanger, we use this graph to find the value of the correction factor F. Using this reference figure as a guide, we can compute for the value of the temperature ratio P and for the temperature ratio R. For two shell passes, multi-tube passes heat exchanger, we use this graph to find the value of the corresponding correction factor. Again, using this given reference figure as a guide, we can compute for the values of the two temperature ratios. We can implement the same workflow for finding the correction factor for single-pass cross-flow heat exchangers with both flows unmixed through this graph, and for single-pass cross-flow heat exchangers with one flow unmixed and the other mixed through this graph. Using this reference figures as a guide, we can compute for the temperature ratios corresponding to each type of heat exchanger. In the next video, we will discuss the effectiveness NTU method of heat exchanger analysis.